Alrighty, so a few examples I wanted to go through. I have the list here actually. Page 76, 24678, page 101, number 52, and page 102, 3, 4, 5, and 9. So these are to go along with Newton's laws of motion, which is forces and accelerations included, acceleration being a change in velocity over time. So let's go through these. So page 76. Let's see. You push with a 20 Newton horizontal force. This is number 2 on page 76. Push with a 20 Newton horizontal force on a 2 kilogram box of cookies. Okay, here's my box of cookies. Whatever kind you'd like them to be. And it's on a tabletop, nice and horizontal. Let's see, 20 Newton horizontal force. I push, and I'm going to just draw it from the center of mass. So it's pushing on this side, the left side there. I'll just call it force push. Remember from the notes, I sometimes call that force applied. That's fine. 20 newtons. And the mass of the box is 2 kilograms. I'll even put a little mass box. Horizontal surface, that's good. There's a horizontal friction force of 12 newtons, so this is not a frictionless surface at all. Try to draw it somewhat to scale. So force of friction, it's kinetic friction because it's sliding, and that's 12 newtons. It's negative 12 newtons technically, but I've already drawn the arrow, so there's no reason to confuse the picture anymore. And it says, show that the acceleration is going to be 4 meters per second squared. Well, really what it's saying is just go ahead and solve for the acceleration. Let's see, remind ourselves. Here's our triangle. Force is mass times acceleration. But here we need the net force. So what is the net force? Well, we have a force of the push this way that's 20. Force of friction that way that's 12. The remainder is going to be 8 newtons to the right. So our force, our net or overall force, is 8 newtons. Acceleration, we have no idea. And the mass that is being accelerated is 2. So, let me see, get fancy here. Cover up acceleration, and we find that acceleration is force divided by mass. That overall force is 8 newtons, 2 kilograms. It becomes 4. And the units of a newton are actually a kilogram meter per second squared, so the kilograms cancel out of that. And so those are the units of acceleration, meters per second squared. So it is indeed 4 meters per second squared, and the question asked us to prove that, and we have. Just save this for us. Okay. Now we have number 4. An astronaut of mass 100 kilograms there's my astronaut. A nice big belt buckle. Looks like the Pillsbury Doughboy. Mass of 100 kilograms. The astronaut, 100 kilograms, recedes from her spacecraft by activating a small propulsion unit attached to her back. So here's her spacecraft. And there's a propulsion unit attached to her back. And I pointed in the wrong direction. Propulsion unit attached to her back. Okay. The force generated by spurt from the propulsion unit is 25 newtons. Okay, well it's pushing out that way. Equal and opposite reaction because it's pushing against the particles that it's expelling, which are actually pushing against this. So let's forget that and just assume that we look at this force. So the force is 25 newtons. So call it the force of the jet. 25 newtons. Okay. And it's accelerating her to the left on our plane. Show that her acceleration is 1/4 meter per second squared. So again, it's just saying solve for acceleration. Force is mass times acceleration. Get rid of acceleration, or rather cover it up, sorry. And again, acceleration is force divided by mass. The net force is 25 newtons. And divide that by 100 kilograms. Again, that resolves itself to 0.25 meters per second squared. Proven. We didn't have another force to consider here to find a net force and overall force. So the net force was just 25. All right. Now this one's a personal favorite of mine. Number 6, the bear. It says a 400 kilogram bear grasping a vertical tree. So they try to simplify it as much as possible for us, right? A vertical tree. Let's see if I can draw a bear. Let's see. These are his arms. Looking fuzzy wuzzy. I'm going to have his legs attached too. Okay, so there's our bear. And he's grasping a vertical tree. Ah, I should be an artist. Okay. His mass is 400 kilograms, or his or her. Yep, his or her mass is 400 kilograms. Mass of the bear. That's a pretty heavy bear. And more than 4 times my mass. How much friction force? Oh, well, hold on. There's an important point here. Constant velocity. When you're at constant velocity, means the change in speed is 0. That means, I'll put a little therefore. These little things mean therefore. That means that acceleration is 0 meters per second squared. I've got to close this down. Okay. Sorry, email's bothering me. Acceleration is 0 meters per second squared. And it's very important. Anytime you see constant velocity, it means acceleration is 0. That doesn't mean the guy's not moving, right? Or this gal bear. It just means moving at a constant speed. Now, the important thing for that is that the net force is 0. So that means that the weight of the bear, let me do a different color than that. Okay. The weight of the bear, force due to gravity, the weight, is balanced, equal and opposite, to the kinetic frictional force. So they're equal to each other. So what we're trying to find is what the frictional force is. Well, that's actually easy now, because if we can find this, then that will tell us that. we can find the weight of the bear, since it's balanced by the friction, it'll be the same, just in the opposite direction. So we know that the acceleration is 0, that's fine, but the acceleration due to gravity, what causes the weight of the bear, force due to gravity for the bear, is going to be mass times gravity. So it's 400 times 9.8. Technically, it'd be a negative 9.8. It'd be downwards. I'll just say down. And that turns, well, it's about 4,000. 3,920, I think the answer probably is. Yeah. 3,920 newtons. And so that's the weight down, and so the frictional force is that up. So if this is negative, then the frictional force would be positive, depending on your frame of reference. But the magnitude, the number value, is 3,920 newtons, regardless of the direction. Something kind of similar, except with an acceleration. Now we have a firefighter. Okay, here's our firefighter. Firefighter is sliding down a pole. Oh, it even straightened it for me. Sliding down a pole. Let's pretend that pole's straight up and down. The firefighter has a mass of firefighter of 80 kilograms. And slides down the pole. The acceleration, it's really the net acceleration, right? The overall acceleration is 4 meters per second squared. Because we know that there's an acceleration from gravity that's 9.8, but the frictional force that's involved here, right? The fellow is holding on to this and sliding down, allowing friction to occur by touching it. The frictional force involved is upwards. And so it's going to be the opposite, and it's going to cancel some of that out. So to show that the friction force that acts on the firefighter is 480 newtons. So this brings it a little bit to another level. But here's the idea. If the net acceleration, well, here, it's an acceleration vector, right? So gravity is 9.8 down. The overall acceleration is just 4. Then this remainder is going to be 9.8 minus 4, or 4.8 meters per second squared, up, meaning in the opposite direction of the intended slide, right? Because friction's job is to prevent slipping. Well, it's not doing a perfect job, but it is going against that slip. So then this is the acceleration from friction. It's a negative acceleration, or at least it's in the opposite direction of what we intended. So that's what we would use. If we want to find the force of friction, again, force is mass times acceleration. Cover out force. The force is kinetic friction, mass, acceleration from friction. Let me make this a different color. So the kinetic friction is the object's mass, which is now a person's mass, times 5.8. I'm not going to just trust the book's expected answer, right? 464. Now the book wanted 480. Okay. The book wanted 480, but it's really 464 newtons, and that would confuse you because the book assumes 10 meters per second squared, so that's fine. If you did 10 there, you'd have 6 left over, be 480. All right, one more on this page. Number 8. A boxer punches a sheet of paper in midair. So here's the boxing gloves, right? Let's see. It's a red boxing glove. And there's a sheet of paper. And brings it from rest, so it was just suspended there. Brings it from rest up to a speed of 25 meters per second in 0.05 seconds. So we have a couple things. We have the idea that the initial speed is 0 meters per second. The final speed is 25 meters per second. And that the time it took is a very short 0.05 seconds. So, from this, we get that the change in speed, or if we care about the direction, the change in velocity, is actually 25 meters per second. Okay, change in velocity is final minus initial. And if you recall, acceleration is a change in velocity over time. Well, that's 25 meters per second, 0.05 seconds. Go to your handy dandy calculator if you don't want to do fractions in your head. No reciprocals. Right, 500. Okay. So the acceleration is going to be 500 meters per second squared. So this is the piece of paper is experiencing a very high change in its motion. Originally it was at rest, and outside force acted on it, it was accelerated. So the idea now, I'm going to extend this page slightly. The idea now was the mass of the paper was, what is that? Where am I at? 0.003 kilograms. Very low mass. And so we were asked to find the force, or verify the force. So again, force, mass, acceleration, that overall force we said was, we don't know. The mass we said, 0.003. Multiply that by 500. And it looks like we're going to get 1.5. And I'll just verify it so I'm not confusing myself with decimals, right? We got 2 zeros there, 2 zeros there, 0.3 times 5. I do this too because I like you to see the calculator process. Just in case. Sometimes it helps. You can always pause the screen. And we verified 1.5 newtons. All right. Hopefully you guys are still with me. How long has this gone? 19 minutes. Okay. That's right. It's worth having some examples. Be a large PowerPoint file, though. Okay, 52. This one won't take long at all, actually. 52 on page 101. The velocity of an object is doubled by what factor is its momentum change? Well, momentum is mass times velocity. So if you double the velocity, all you've done is double the momentum. Now, the second part is, what about the kinetic energy? Well, kinetic energy, if you remember, 1/2 mv squared, and this is actually something that was important to us. If you double the velocity, it's 2, 4, right? Becomes 4 times as much, 2 squared. And you quadruple the kinetic energy. And that's just kind of a review for you. So whereas the relationship between kinetic energy and velocity was a complex relationship, the relationship between momentum and velocity is what mathematicians call a simple relationship. So finally, 102, we have a few problems left. All right, so I stepped away for a few moments there, as you can probably tell by the timestamp. So page 102, number 3. 8-kilogram ball. Mass, 8 kilograms. Rolling at 2 meters per second. It means in this direction the velocity is 2 meters per second. Bumps into a pillow. Okay, so there's a pillow, and it's brought to rest in a time of 0.5 seconds. So it sounds like this is going to be a momentum impulse question, right? Show that the average force exerted by the pillow is 32 newtons, and then how much force does the ball exert on the pillow? So it's really using this fat mav. Momentum is mass times velocity. Impulse is that average force times the change in time, which this is change in time either way. And then change in momentum is the same thing, mass times the change in velocity. Well, it's going to go from 2 to 0. So final is 0, initial was 2. So the change in velocity is going to be a negative 2 meters per second. I'll just put that in parentheses. You don't always have to carry it through. 2 meters per second. The mass we know. So the change in momentum is going to be the mass, 8, times the 2 meters per second, or it looks like 16 kilogram meters per second. And that's negative. And then we remember that impulse is the change in momentum, so negative 16 kilogram meters per second. Again, the only reason I'm putting the negative in parentheses is because I just keep it off to the side. Change in time we know, so force is actually going to be 16 divided by 0.5. Looks like it's going to be 32. Again, negative because it's in the opposite direction, newtons. And that was the force exerted by the pillow on the ball, so it exerts it to the left, which makes sense. Verified. Number 4. A car crashes into a wall at 25 meters per second. Here's the car. 25 meters per second was its initial speed. Its final speed, well, it's going to go to 0. So if it goes to 0, then the change in velocity is again 25 negative, right? Meters per second. And it's brought to rest in 1/10 of a second. Very short period of time. So that the average force exerted on a 75 kilogram test dummy by the seatbelt is more than 18,000 newtons. Well, that shouldn't be too hard, right? Here's the dummy. Here's the seatbelt. Basically, the seatbelt, it means it's attached to the car very securely. So whatever acceleration or deceleration, if you will, that the car is experiencing, then the dummy is going to experience as well. So 75 kilograms is the mass of the dummy. Mass of the car doesn't matter here because that went into determining the amount of time it took to come to a stop for this change in velocity to occur. So, acceleration, change in velocity over time, 25 meters per second over 0.1 seconds. Looks like 250 meters per second squared if you do your math. And then again, force is mass times acceleration. The mass is 75. Acceleration is 250, technically negative to the left. And it looks like it will definitely be more than 18,000. Let's plug that in just to see how close we get. Yeah, 18,750. And technically, again, it's negative. It's to the left. Okay, getting there. Two more. Number 5. At a ball game, a baseball has a mass of a mass of 0.15 kilograms. And it's moving at a speed initial, of 40 meters per second. And then it's grabbed by a fan. Right, that's a fan, right? Oh, wait, no. That's a fan. Grabbed by a fan. So the impulse applied, or in other words, find impulse, J equals question mark, and then you're given the time. So they actually want you to do this kind of separately. So the time it took to stop was 0.03 seconds. That's from the time you make contact with the glove. And then we have to find the average force. So it would again be fat math. So here, they're trying to trick you a little bit. Impulse is just the change in momentum, which is mass times the change in velocity. So 0.15, the change in velocity was going to go from 40 to 0, so it's, again, technically negative 40 meters per second. Looks like it's going to be, what's that, 6? Yeah. Again, negative 6 kilogram meters per second. So that's the impulse or the change in momentum. Now, FatMav says F delta T, remember this is always delta T, it doesn't really matter, it's the same thing. Time or the passage of time is all the same. Mav. So it means that the force and the change in time is equal to the change in momentum. Well, we already found the change in momentum right there. Okay. So it's going to be 6. And again, I just dropped the negative now and then because we know which direction it's going to be. It's going to be outwards this way. It's the stopping force. And the force of the ball in the catcher's hand is in the opposite direction, which is the one we're finding, so it'll be positive. So the force is going to be 6. We divide the time over to get it away because it's cramping F's style. 0.03 seconds. Okay. And it doesn't quite look, well, that's right, because it'll be a fraction. It'll have a few extras. Yeah. It looks like exactly 200 Oops, let's get that there. 200 newtons. Good. Then the final example I wanted to put together for you guys is number 9 on page 102. Comic strip hero Superman meets an asteroid in outer space. Here's Superman. Okay, here's the asteroid. Let's see if I can draw the asteroid. Okay, fanciful. And he hurls it at 800 meters per second, which they say is as fast as a bullet. This is kind of like an explosive situation. It's like his arms, his muscles are springs, and the two objects were one, and now they're exploding outwards away from each other. So the asteroid's 1,000 times more massive than Superman. So m equals 1,000, a little m, right? Here's the mass, little m. We don't know what it is. We just know this is 1,000 times more. So this is conservation of momentum, basically. If this speed here, I'll call it big V if you can see that, is 800, with a small mass, it's a simple relationship, right? A linear relationship. Momentum is mass times velocity. Then the momentum has to be balanced in the other direction, because the net momentum, the overall momentum, has to be 0, because total momentum is boring. Total momentum doesn't change. So if it's 800, 000 this way, then it's going to have to be 800, 000 that way. So you make up for a mass that's 1,000th, 1,000th of the asteroid's mass by having 1,000 times greater speed. And then conservation momentum is appeased. All right, that's it.